Hi everyone, welcome to the AWM pitch seminar. Today we have speaker Charlotte Beckford. She is a PhD student from University of Tennessee at Knoxville. Her topic today is a hybrid model of winter trick epizootics on moose. You can start.
Hi, everybody. Thank you for that introduction, Farjana. I'm so sorry, I went all the way to the end. As was just explained, my research project is about a hybrid model of winter tick epizootics in moose. And so currently the project is over at this moment. We're kind of like preparing to publish, but I was working with another graduate student, David Elzinga, and his advisor, Dr. Christopher Strickland at the University of Tennessee, Knoxville, where I am currently a PhD student. I think I'm just gonna not do this slideshow again because it was not liking that. Okay, so anyways, the motivation behind this project is that climate change is heavily favoring tick populations. So due to warmer temperatures and shorter winters, later onset of winter and then early onset of spring, that means that the tick populations, they have more time to find hosts. They have, and they're also more likely to fall off of the host when there's no snow cover, which means that they have a higher likelihood of surviving and reproducing, which means that the tick populations are increasing. And so specifically the winter tick, Dermacantor albopictus, they do parasitize various hosts, but their evolutionary relationship just means that they're really well adapted to parasitizing moose. So the moose population is being really affected by this enhanced tick population. So epizootics occur when there is this year where there is a particularly high tick population. And during epizootic years, yearling and adult tick-induced mortalities are higher. They're occurring at a higher frequency. And there's also decreased fecundity. That's also another consequence of the tick parasitism, which means that these years of tick epizootics, which are becoming more frequent due to climate change, they actually have long-lasting effects. DeBow 2020, they concluded that they believe that the decreased fecundity can last up to 3 years. So we see how these particular years that due to climate change, the tick population is really high, that drives the moose population down, not just in that year, not just increasing the winter mortality in that year, but it's also affecting subsequent generations of moose. Now, tick moose dynamics are very seasonal dependent. So the ticks, their lifespan is 1 year. And so during that year, they're born in, the eggs are laid in late spring, early summer. Then they hatch in late summer, early fall, and they begin what's called the questing period, during which the ticks, they climb up vegetation to approximately the height of a moose shoulder, and they form these huge clumps, and they just wait until a moose walks by. And then when a moose walks by, they detach themselves as a clump, and they attach themselves to the moose. So then during the fall and winter, they are attached on the moose, they're present on the moose, and they're parasitizing the moose. They're sucking the moose's blood. They create open wounds, which leave the moose more susceptible to infections. And at the same time, during the winter, moose periodically go through a kind of starvation season because there's less food availability. So they really rely on the fat reserves to sustain themselves. But if at the same time they have to be constantly replenishing their blood supply, that decreases their overall health and well-being. And so then in early spring, that's when the ticks detach themselves. And so again, if they detach themselves and they land on snow, they're less likely to survive and successfully lay eggs, which will start the cycle over for the next year. But with climate change, with snow melt occurring earlier, with snow cover being less likely, that means that they're more likely to land on terrain, which they will survive, and then they can lay more eggs and those eggs survive. And then also with the later onset of fall, that means that they have a longer questing period. So they have more time to find a host, because if they haven't found a host by the time that there is the first snow cover, most research, they concur that the ticks will die. They're not going to successfully find a host for that year. Now, this is an increasing concern in the northeastern United States. Wildlife departments in Maine, New Hampshire, and Vermont have started moose treatment and monitoring programs. And so because of that, there's this new influx of data, which is really great for our purposes of modeling. But in general, there has been little attempt to model tick moose dynamics. One reason is that it's very difficult to get data specifically on the ticks and then model the ticks. Getting data on ticks is difficult because they're small, they're in the environment, and then modeling them, something that we encountered ourselves, is computationally expensive because they exist in such large quantities and they're such a small individual, but then their population size are so big. One notable exception to the lack of models was Healy 2018 created an Asian-based model of these dynamics. And so they were focusing on the effects of the densities of each species and weather conditions in producing epizootics. Again, going back to the idea of like how snow cover is so closely related to the ticks being favored or not. And in their future work section, they recognize that the moose behavior, as well as the ticks behavior, also vary seasonally, because during the fall, for example, that's when the moose rutting season occurs. And so that's one of the reasons why moose are such a susceptible host of the ticks, because they're rutting at the same time that the ticks are questing. So they're more likely to come in contact with the ticks, not just some ticks, but many ticks, because they're in the areas where the ticks are forming these clumps. And so that's when you get the scenario where moose are being parasitized by tens of thousands, hundreds of thousands of ticks. And that's where you get like this really high blood loss, they're grooming themselves and they're losing their fur and they are really sick and might die.
I'm unfamiliar with moose terminology. What's rutting?
Sorry, rutting is that's like their mating. That's when they're searching for mates. And I think also I should probably know this. I think also maybe male moose fight during that time as well as they compete for mates. Not entirely sure, but because it is like during the mating season, they are moving around more than during other seasons.
Okay, thanks.
So for this first phase of our research project, the question that we were focusing on was what are the effects of changing the season lengths due to climate change on the moose and tick populations? So the idea, we kind of identified like 3 principal seasons that were important for our model. So there's the questing season, which again is when the ticks are finding hosts and the hosts are being parasitized. So that we refer to as autumn. Then there's the winter season, which is when the moose are parasitized. And so that's when they are dying because of parasitism. So they might be experiencing other infections like comorbidities. They're also during that starvation period when they're susceptible. So that's when like tens of these small, tiny ticks can actually kill moose. And so that's the winter. And then the rest of the year, we just refer to that as summer. That's just a linking time. There's no major moose tick dynamics. So we constructed a hybrid model that again captures these seasonal dynamics. There are 3 systems of continuous time differential equations for each season: the autumn season, which is questing, the winter season, which is when moose death occurs due to the ticks, and then the summer season, which just links the rest of the year. And then between those continuous time differential equation models, we have discrete time pulses. And so the goal for this phase of the project was that we wanted to create a model that was simple enough such that it was analytically tractable. And so that led us to make some simplifying assumptions. For example, this model, we were assuming that the tick population was at a high enough constant level that infection was a constant environmental rate. So this model, we consider it to be really good for representing epizootic years when that is, those are feasible assumptions. So this is the model. The time is measured in years. We begin the model in year N, and then it starts in the winter season, which has a length of omega. Then it goes to the summer season, which has a length tau, and then the autumn season, which has a length alpha. And again, we were interested in the lengths of these seasons in these models. So just to go over some of the model parameters, mu is the natural mortality rate of moose. So moose die at a background natural mortality rate in every season. Nu is the tick-induced mortality rate. So tick-induced mortality only occurs in the winter, and it only occurs in infected moose. Gamma is the recovery rate. So after all of the ticks fall off during that discrete pulse from winter to summer, we actually have the infected moose recovering at a constant rate gamma. And so that's to reflect the idea that they're not just going to become well all of a sudden when all the ticks go away. They might be fighting off some comorbidities. They still have these open wounds that are susceptible to disease. So it might take some time. Then beta is the questing rate that occurs in autumn. So that's the transfer rate of susceptible to infected moose. And so these are also our pulses. The winter to summer pulse, it captures an important instantaneous, what we model as an instantaneous event. We model the reproduction of moose as instantaneous. They reproduce at a rate R. And then there's no other major moose tick dynamics that we were capturing this model during the pulses. Everything else we were considering as being continuous time. And so those pulses were just linkers between our systems of differential equations. And again, we were making this model as simple as possible such that it was analytically tractable. So we do have a lot of assumptions and generalizations, but that was, we were sacrificing that for the analytic tractability. Now, we were able to reduce this model by collapsing or discretizing it. So how we did that is we solved explicitly the continuous time differential equation systems for each season. Then we picked initial conditions at the beginning of the very first winter season, like we picked an initial infected moose population and susceptible moose population. We were then able to project that population to the end of the first winter season because we had the solution to that system. Then we applied the pulse from the winter season to the summer season. Again, because we had the summer season solved, that pulse, it was then the new initial condition for the summer season. We solve for the end of the summer season and just rinse and repeat for the autumn. And then you have like a year-to-year pulse. So rather than having these 3 pulses in 1 year, we were able to collapse it. So it's just one pulse from the beginning of the winter season to the next beginning of the winter season. We also conducted stability analysis of the model. As expected, the only equilibrium is extinction equilibrium, and that made sense because, again, this model was assuming that that it's epizootic conditions, that the tick infestation level is so high that it's just a constant environmental background rate. And then we use jury condition to find a condition on the reproductive rate of moose for the stability of this equilibrium. And it is this lovely expression right here. And so obviously, like wildlife managers, they can't just increase the reproductive rate of moose. But this upper bound on the reproductive rate, it shows that even under epizootic conditions, extinction is unstable if the reproductive rate of moose is sufficiently high. So that's good. It can help us analyze if the moose populations will survive, maybe by transferring in moose from other areas. They can increase the reproductive rate in one area by increasing the potential number of mates. So in that way, they could potentially save populations. So one way that we analyze this result is we created these simplex plots that show at different levels of the questing rate beta what combinations of the season lengths result in the extinction equilibrium being unstable and the extinction equilibrium being stable. So the questing rate, unfortunately, again, because there's not a lot of research on ticks because they're small and difficult to observe, let alone model, that was not something that we were able to find an estimate for in the literature. So we just kind of varied that parameter widely to account for that. And then the green region is the combinations of the length of the summer, tau, the length of the winter, omega, and the length of the autumn, alpha, where the extinction equilibrium is unstable, and then the gray is where the extinction equilibrium is stable. So green is good because it's unstable, but that means the moose are surviving. Gray is bad because it's stable, but that means that the moose are being driven extinct. And so one thing that we noted is that the season length combinations where the extinction equilibrium is stable is really centered around that lower right the lower right corner of the triangle, and that corresponds to the a longer autumn season, the longest autumn season. And so that was something that was interesting because the literature, they were all saying that the shorter winter season due to climate change is what's favoring the tick population and what's leading to the damage of the moose population. And we were actually finding in our model that a slight distinction, it's not the shorter winter season, it's the longer autumn season. Now, of course, the two are related because if you have a shorter winter, well, you have longer periods for the other two seasons. So that's correspondent to a longer autumn. But we were really finding that it's not just the shorter winter, it's the longer autumn that's responsible. And so one thing that to know also is that the red dot is the current literature, all of the values that we were able to find. The red dot is where the moose population currently is. So we saw that at beta equals 0.5 and beta equals 1, where the moose population currently is within that zone where the extinction equilibrium is unstable. So that's good. But at a higher beta equals 1.5, this is actually, I could not make my TIC-C circle any smaller. This is actually slightly in the gray region. So it is just over that limit where the extinction equilibrium is stable. So we see that, again, we can't estimate this questing rate, but if the questing rate is high enough, where the current distribution of seasonal lynx currently is, the moose population extinction is stable. Now, this was just like the first phase of our research project. After this, we created a more complex model, which was not analytically stable, but which we performed numerical computations with. And so that one was also a tri-seasonal model, but it was a 5-class model rather than just the 2 moose classes. We modeled susceptible and infected moose as well. We also modeled emaciated moose, which are moose that are suffering long-term suffering due to repeat tick infestations. And then we explicitly modeled ticks. We modeled questing ticks, which are in the environment, and host ticks, which were present on the moose. And so that model, the questions that we were addressing is at what time and rate should hunting be performed to protect the moose population from severe tick parasitism? Because maybe not the only, but new programs are suggesting new management strategies. But the only widely used one currently is to hunt the moose population, because by keeping that moose population contained at a low level, that actually prevents the tick population from being able to reproduce at huge amounts, which will then drive the moose population to extinction. And then the other thing is because these wildlife institutions and programs are interested in protecting the moose population, there are some novel management strategies that are being proposed. So we wanted to investigate the feasibility of them. So we really saw this numerical model as being more applicable by the wildlife management people. And in that model, we found that hunting to limit the herd size is effective, but only under epizootic conditions. So if you're not actually under conditions where the moose population is in danger of going extinct due to the tick parasitism, well, hunting them just limits their population size. So that's not helping. And we also performed sensitivity analysis using Sobel sampling. And at the time I made this presentation, we were continuing to work on this phase of the project, but since then we have finished. So my co-collaborator is currently working on preparing the publication, so that's exciting. These are some of the references that we used, and I am just so grateful to everyone I worked with on this research project, David Elzinga and Dr. Strickland, and to all of you for letting me present. And I'd be happy to answer any questions if anyone has any.
Thank you for your wonderful talk. I'll stop recording now first.